This is Geometry, Unit 5, Lesson 1, Parallel Lines and Transversals. So let's take a look at the definition of parallel. Parallel means two coplanar lines are parallel if they have no points in common. If you have two lines that one runs like this and another one runs like this, no matter how long they get, they will never intersect. They have no points in common. So those lines would be parallel. Now, you could also be parallel if they have all points in common. If you have one line laying on top of another line, let me do it in a different color here. If I had another line that laid on top of this line, like so, it would be the same line. Those two lines would be parallel because they're actually the same line. So all points in common, the lines coincide. Those two lines would actually be parallel. Okay, now let's take a look at a postulate about parallel lines. This is an important postulate because it feeds into our process of using rigid motion. Now, through a point not on a given line, there is exactly one line parallel to a given line. So if you are given a line and you want to draw a line parallel to it through a certain point, there's only one actual line that will do that. So if you were to draw the line in, there's only one line that you could draw that would be exactly parallel to this line. All right, there's no other way I could draw a line to make it parallel to this line that would go through that point. So that's an important idea. Now, the next piece of information that we need to know is a transversal. A transversal is a line, sometimes called T, that intersects two other lines, L1 and L2, at different points. So if I look at my two lines that I drew parallel here, and if I draw another line through it, like so, that would be a transversal. So this is line 1 and line 2. This would be my transversal. Notice that the transversal will intersect the two lines, parallel lines, at two different points, here and here. Now, when you draw a transversal on pairs of lines, you create different kinds of angles. Notice here we have two lines here drawn. We don't know if they're parallel or not, but we have a transversal T going through them, L1 and L2, like so. Now, we have the different kinds of angles based on where they are around the lines. There's 8 angles labeled here. When you have the two lines and draw with the transversal, 8 angles are formed. Now, the first type of angles are called corresponding. Corresponding means angles in the same relative positions, or else in the same place on the lines. So if I look at angle 1 right here, and I look at the other line, what angle is in the same place on the other line? Well, this one's in the upper right on this line. Angle 5 would be in the upper right on that side. That's in the upper right. So what angle would be corresponding to angle 2? Well, 2 is here. That means it's on top of the line here, so it should be at 6. Angle 6 is right there. All right, angle 3 will correspond to angle 7. It's underneath the line here. It's underneath the line here. So it'd be angle 7. And then angle 4 here would be corresponding to angle 8, would be right there. They're in the same place on the two sets of lines. That's corresponding. The second type of angle are called alternate interior angles. Now, alternate interior basically telling you where the stuff is. They are angles between the two lines. So here's your two lines. And on opposite sides of the transversal. So they're written as pairs. So the angles 3, 4, 5, and 6 are in between the parallel lines. Now, not only are they between the lines, they are on opposite sides of the transversal. So if I look at angle 3 here, what would be the alternate interior angle to angle 3? Well, on the opposite side of the transversal, that would be over here. That would be angle 5. And then the other pair would be angle 4 and angle 6 would be these two right here. Those would be alternate interior angles. Now, the final type of angles that we have with these two kinds of lines with a transversal are same side interior angles. Now that tells you exactly what it has. Interiors inside the parallel lines, angles between the two lines, and same side means on the same side of the transversal. So if I look at angle 3 right here, what angle is on the same side of the transversal and still between the parallel, or the two sets of lines? It would be angle 6. So angle 3 and angle 6 here are same side interior angles. So angle 4 here would be a same side interior angle with angle 5. So those are the kinds of angles that are formed when you have two lines cut by a transversal. Now, there are some certain facts that we need to know before we get into what happens when you have parallel lines and angles. Let's look at what happens when you have a line that's being translated. So if I have a line that is translated in its own direction, its image will be the same line. So I have line P right here. Here is line P. And suppose I wanted to translate line P so that it ends up where P prime is, so it's still in the line. If I translate like this, and I move it down like so, the image will be the same line. If you start on the same line and you slide the same way, it's going to be the same line. Now, but if two lines, L1 and L2, are parallel, and P is any point on L1, and Q is any point on L2, if I translate this along PQ, the vector PQ, this line, go down here, will end up on this line. Now, if the lines are parallel, P ends up at Q, and you can see the image will coincide with L2. They line up perfectly. But if the lines are not parallel, you can't slide this down and get it to line up with L2. There's no way you could do it just going along a vector. So, the important part about this is if the lines are parallel, anything that is up here will be the same as it is down here. That brings us to some important points that we have about the angles that are formed. Now let's go back to the corresponding angles again. We are going to look at what happens with corresponding angles when the lines are parallel. We are given L1 and L2 are two lines here, and transversal T intersects L1 here at P and L2 at Q. So this T comes down and hits here. If L1 is parallel to L2, if these two lines are parallel, and under the translation from P, the vector from P to Q. So if I took L1 here, and I slid it down here to end up at Q along this vector, isn't this going to coincide perfectly? So that means the transversal is still going to be the transversal, so the image of T is still going to be T, and the image of L1 will end up being L2. So the lines are going to coincide. All right, by doing the translation along the vector, which is actually the transversal, you end up on the same line. So that means angle 1's image will be what angle? It will be angle 5. And the image of angle 2 will be angle 6, etc. Now, if this is the same image, didn't we say the properties of a translation, angle measure stays the same? That means that angle 1 will be congruent to angle 5, the measure, and angle 2 will be congruent to angle 6. And all the other angles. 3 will be congruent to 7, 4 will be congruent to 8, because angle measure is preserved in a translation. Now, if L1 is not parallel to L2, then under the translation along PQ, the image of T will still be T. If you slide this down, but the lines aren't parallel, but the image of L1 will not be L2, and angle 1 will not equal angle 5. So if we flip back here for a second to this diagram right here, if I were to slide this line down like this, down this vector like so, is it going to line up with L2? No, it's not. So then the angles could not be congruent. That's basically what that's saying. So, what's special about corresponding angles? Corresponding angles are congruent. So by using our rigid motion that we just did for the translation, we have just proved when parallel lines are cut by a transversal, corresponding angles are congruent. Now, the converse of this theorem, which means if you switch it around, if two lines are cut by a transversal and the corresponding angles are congruent, the lines will be parallel. So we can use this theorem two ways. If we know we have parallel lines, we can say the corresponding angles are congruent. And if we know that the corresponding angles are congruent, we can say the lines are parallel. So that's a very handy reasons that we have that we can use in proofs later on. All right, so knowing our facts about corresponding angles, let's see if we can find the measures of these angles. If I know one of these angles, I actually know all 8 of the angles here, and let's prove what we know. So we know that this angle right here is 130. Now, what do we know about corresponding angles? We know corresponding angles are congruent. So 130 sits on top of this line right here on the left-hand side. So corresponding angle would be up here. This is 130. So we know that so far. Now, remember that these are all lines. Do we know anything about this angle right here? Well, this angle and this angle together are adjacent angles that make a line. What do we know about them? They're supplementary. So that angle right there is 50 degrees. Now, would that also be true for this angle up here? Yeah. These two add up to 180, and aren't these two right here corresponding angles? So that would be 50. All right, so now we've got 4 of the 8 angles. We're halfway there. What do we know about this angle right here? Well, we know that it is supplementary to this angle, which is 50, and it's also equal to this angle over here because this is a vertical angle. Aren't these vertical angles? Intersecting lines form vertical angles that are congruent. So this one is 50, and by corresponding angles, if the lines are parallel, since these two lines are parallel, if this one's 50, this one's going to be 50. And finally, over here, well, we can say that these two are supplementary or these two are congruent. So if this one's 130, that one's going to be 130. Notice the zigzag. All of the angles that are diagonal from each other are the same both ways. So if you know one of those angles using corresponding angles, vertical angles, and supplementary angles, we can find all measures of the angles. Now, if I were given this picture, this is not to scale obviously because these are all different angle measures, which of these two lines are parallel? Well, look at the angle measures here. We have 47, 48, 49, and 48. Which two would be parallel? Well, which ones have corresponding angles congruent? It would be this one and this one. B is parallel to D because the corresponding angles are congruent. Since the corresponding angles are congruent, the lines are parallel. Okay? Now let's see if we can prove if alternate interior angles are congruent. They are. When parallel lines are cut by a transversal, alternate interior angles are congruent. We're going to prove it. So we are given that L1 and L2 are parallel and transversal T given here. Now we want to prove a pair of alternate interior angles are congruent. What are a pair of alternate interior angles? There's 2 pairs. What's one? Let's say angle 3 and angle 5. Let's prove that angle 3 is congruent to angle 5. Let's prove that. So we are trying to prove this angle is congruent to that angle. That's my goal. Now, what do we know if we have parallel lines? We just learned about corresponding angles. Can we say something about angle 3 or 5 and a corresponding angle? Well, let's look at angle 5. What angle corresponds to angle 5? It would be angle 1. Angle 1 is congruent to angle 5 because if lines are parallel, corresponding angles are congruent. Okay, so we know that angle 1 and angle 5 are congruent. Angle 1 and angle 5. We know those are congruent. So we have something about angle 5. Now we need to know something about angle 3. Well, what do we know about angle 3? Well, isn't angle 3 congruent to angle 1? What kind of angles are those? Well, aren't those vertical angles? Intersecting lines form congruent vertical angles. All right, so we know that 1 and 3 are congruent. Well, look what we have here. 1 is congruent to 5 and 3 is congruent to 1. So by substitution, angle 3 is congruent to angle 5. It could also be transitive. So we have just proved that that is true. So we now know that if you have parallel lines, alternate interior angles are congruent. Now the converse of this theorem is also true. If you have lines cut by a transversal and the alternate interior angles are congruent, the lines are parallel. Save this for the next lesson.